Thank you. Thanks. So welcome to my talk on Magnetips. This work was done by myself from the University of Copenhagen with my colleagues Jarrod from the University of Monash and Paul Strohmeier, Sebastian and Kasper Hornbæk, also from the University of Copenhagen. Okay, so recent work has looked at increasing the interaction space of mobile devices, and in particular this looks at kind of tracking the finger in a space surrounding the device. So in addition, people have also tested various ways to have output, such as visually off the screen, also to match the input location. However, creating haptic devices that work around devices in midair and so on is challenging in a mobile setting. And so that's largely due to their size and sort of difficulty in producing haptics with these techniques, like for air vortices and with the ultrasound having a large array. And haptic feedback can be important for several interactions, such as eyes-free and also to midair. So we developed a solution to this, which we call Magnetips, and this enables simultaneous input and output around the device using magnetism. And we show that this technique can support a number of interesting interactions. So how does it work? Well, first let's look at the input. So there are different ways to do magnetic tracking. So there's active magnetic tracking, as Phoenix has showed by Chen et al. And then there's also passive magnetic tracking using permanent magnets. And a neat trick you can do is that you can actually actuate the magnet, the passive magnet as shown here, using an external coil. And here's a clip of this in slow motion, so you can see kind of how it would vibrate as you actuate it by a nearby coil. Okay, so looking deeper into the hardware, we've got the sensor board, which consists of 4 magnetometers, a gyroscope, and an accelerometer. And the actuating component is simply just a coil with some circuitry to drive it, which I'll show later on. And we made a conscious decision not to include a core to generate the magnetic field, since this is easier then to embed into wearable devices, mobile phones and so on. And we actually made a coil kind of a similar size to the Apple Watch 3, so you can fit it around the perimeter of the device. And the sensors are actually made to fit within the footprint of this device as well. But we can imagine Magnetips being sort of integrated with a number of different mobile form factors as well. So how does the tracking work? Well, it has 4 magnetometers with a 1 kHz sampling rate, and that's actually quite crucial, as I'll talk about more in a bit. And it's quite a similar setup actually to the setup used by Chen et al. And Nexus. So we've actually used that algorithm as a baseline implementation, which uses kind of a field strength to kind of work out and triangulate the position. So here's a clip of the tracking in action. So in this clip, the device is actually placed beneath the phone. So this demonstrates that it works through kind of ordinary devices. And now this works when the device is static. However, I'm now going to show you a clip of what happens when the user moves their wrist. So what happens when the device moves is that the magnetometer values change. So if you pay attention to this bit here, you'll see in a minute that the values will shift around. And this is a bit tricky when it comes to calculating the position of the magnet, since the sort of baseline values of the magnetometer are skewed. So to get rid of this effect, we first calculate the orientation of the device, as you'll see on the left-hand side of the screen. And we do this using the accelerometer and the gyroscope data. And then that can be used to infer what the baseline magnetometer value should be. So that lets us cancel out the element of geomagnetism, which can skew the device in cases where the device is actually moving. And as you see when we turn it on, the values of the magnetometers are close to 0. Okay, so we did an evaluation to test the performance of this with and without our geomagnetism cancellation algorithm. So we used an OptiTrack to track both the magnet and the sensor base. And in this case, we just simply did the tracking of the magnet when the sensor base is static. And in this case, as you might expect, as the interaction volume increases, as the input space increases, the sort of average error between the ground truth and the estimated position of the magnet gets larger as well. And then we tested a case where the magnet is fixed above the device, so it doesn't move. So the magnet is static in a way that it's always static relative to the sensor base. And in this case, we can use our geomagnetism cancellation algorithm. And as shown in this graph, the darker bar shows when we turn our algorithm on, it improves the average error. And in the last case, we have a more realistic scenario where you would be moving the base around. You don't usually have your wrist completely still for the interaction, and the magnet is moving too. And in all these cases, our algorithm shows an improvement. So now I'll explain quickly how the feedback mechanism works. So the circuitry is somewhat simple. Only requires a coil, some power, can be used a battery, and a motor driver, and some sort of controller to input the signal. So what does the signal actually look like? So here's an example of such a signal that we will put into a coil. And it's this flip in polarity that creates a displacement of the magnet. So this kind of change in current is actually what creates this change in magnetic field. And we do this for a number of times, and we call this like a pulse burst. Okay? And then we have some time in between where we enable tracking of the magnet. And through our sort of evaluations, we found that the minimum sort of time that you need to enable simultaneous haptic feedback and tracking is 4 milliseconds with our implementation, but this is at least a minimum bound for future technology. And then we can carry on doing another sort of haptic pulse, and then so on and so forth. But we found that the haptic feedback is quite weak, and that's probably due to the fact that we're not using an iron core, so it's just a coil by itself. So we wanted to kind of optimize the parameters of our signal to give us a stronger haptic feedback. So what variables can we use to optimize the haptic strength? Well, we have the signal duration, so how long is a pulse burst, and also we have the length of a single pulse within that burst. And we varied we had 4 different variations of the signal duration, but we made everything fit in within sort of 16 milliseconds, including the tracking, so that we have a minimum of 62.5 hertz tracking rate. So this is actually 62.5 hertz tracking and also continuous haptic feedback that is possible here. And also, of course, we had a number of different pulse lengths to vary. And for this study, we just simply had the user kind of put their finger in a static position above the coil and gave them different haptic signals. And the users gave their perceived strength as a rating. I'm sorry for being a bit lazy, but this is a graph from the paper. I couldn't find a better way of putting it. But the important thing is that actually we just found out that the best parameters for maximising perceived strength of feedback is a 12 millisecond duration with a 4 millisecond pulse length, which aligns with what people have actually found with vibration stimuli in previous work. And then we use these values to find what the range of feedback is. So, how far can we go from the coil to actually still feel it? And for this study, we had a blindfolded user and a modified 3D printer. So, and here's another graph from the paper. It just shows the perceived strength versus the distance from the center of the coil. So this dotted line shows that it roughly kind of fits the inverse cubic relationship. That is, for magnetism, the magnetic field strength roughly falls off as an inverse cubic relationship. But we notice that towards the closer to the coil, there's some non-linear behavior. And at up to about 56.6 millimeters, the signal can be clearly distinguished from those ones further out, and we consider this to be the kind of working range of our haptic feedback. So, what can we do with this? Well, of course, we can provide haptic feedback and tracking in 3 dimensions. So you can imagine you have virtual elements around the device, and you can feel them. And there's a lot of different interactions that may or may not be useful from that. We can also support interaction through materials, even our own bodies, in fact. So we have an application where we envision that people can actually touch the skin on the other side of their wrist, and this is kind of like a bit of a strange see-through / on-skin interaction. And neither the haptic feedback or tracking is occluded by many common materials. And this is one benefit of using magnetism for both things. I mean, you don't have to use magnetism for both things, but we feel that actually it aligns quite well. And this principle of working through materials can also be used to support interactions behind the device. And of course, such as materials such as clothing or bags. And the feedback is quite helpful to facilitate eyes-free interaction, which is particularly useful in cases where your device might be hidden away in your bag or something like that. So let's talk about some of the limitations and future work that we can do here. So the perceived strength of feedback varies across the body. Okay, we saw that it kind of drops off as your finger moves away, but you might not want that. So we could look at having normalizing the strength of feedback across the volume. And once we've done that, we could possibly try to have varying levels of strength, feedback strength. The coil, the design of the coil is, we didn't really investigate changes in that very much. I think it's quite a complicated topic. There's various shapes and sizes that this could take, but we can imagine, you can have grids of them as well if you want to increase the power efficiency, or if you want to have a kind of stronger feedback in some areas. And in this case, we're thinking about, maybe putting it inside a phone so you would have multiple coils within that. We also kind of tried anecdotally using cheap charging coils. And you can feel similar but kind of weaker, more diminished sense of feedback with that. But in the future, we could possibly think about designing coils that would accommodate both charging and haptic feedback. Thank you for listening. I'll take any questions you have.
We have a few minutes for questions. So if you have any questions, please walk towards the mic and speak in the mic. Well, yeah, I have a few questions now. So you mentioned the limitations of coil design itself, but I roughly remember the number of loops in point design would sort of have different effect on this trend.
Yeah.
So what are your reflections on that?
Yeah, definitely. You'll find any optimization in sort of transformers and stuff like that. So it creates the return to the stronger.
Okay. And the second question that I had was like, when you mentioned the error, what was exactly the task? Like what error was actually measured?
Which the tracking evaluation.
Yeah, doing the tracking evaluation, you said with your geomagnetic cancellation algorithm, the accuracy sort of improved.
Yeah.
How did you measure the error?
Yeah, so that was simply an accumulated average error between the ground truth, which is the off-track position of the magnet, versus the what we calculated with.
Also, the off-track track setup was acting as a baseline for that.
Exactly.
Okay. Yeah. Well, thanks again for coming to talk.